Good morning, everyone. Welcome to day 3 of Chicago Roboto, or I should say good morning, afternoon, and evening, depending on where you are. You're in the home stretch. We've got some awesome talks today. I hope that you were able to get some work done, answer emails, quash some bugs, commit some changes, anything you needed to get done today before all of our talks have got started. First up, we've got Wojciech with the magic of ADB and Android Shell. I hope everyone has a great day. Remember, if you have any questions, they are below here in the screen, the Slack channel. Each session has its own Slack channel. So even if you can't see them in the sidebar of Slack, if you just go to channels and click on the plus, you can browse all of the available ones. We will be back live after Wojciech's talk to answer questions live. So feel free to type them in as he goes, and we will tackle them all. And with that, Hello, Wojciech. How are you?
Hello. Well, it's afternoon here in Poland, so yeah, I'm already after my work. I've committed a few changes.
Perfect.
So be safe here.
Yeah, so, yeah, it's dinner time, right?
The technical question: will these questions be available in my chat here, or do I have to join Slack?
You don't. If you want to join Slack, that way you can keep answering them after your talk. But I'll read them out, so you don't have to worry about paying attention to them during your talk. So you just do your talk, and then I will come back on at the end and read them off, and you can answer them live.
Great.
Awesome. All right, take it away.
Yeah, thank you. So my name is Wojciech Sadurski. I will tell you a few of the cool things that you can do with Android Shell and ADB that you may find helpful. So first, a few words about me. I'm a technical project leader at TiVo, which has now recently joined forces with Xperi. So now it's technically an Xperi company, and I've been in a love and hate relationship with Android since late 2013. And I love Kotlin, I love clean architecture, and I love to really understand how things work under the hood. The project I'm working on at TiVo is TiVo Stream 4K, which is a streaming dongle that you plug into the back of your TV, which runs Android TV, and it runs an application which aggregates content from various different streaming providers, and it suggests you different content based on your previous viewing habits. And you can purchase this dongle on Amazon and in Best Buy for like $50 now, I think, but this promotional price will end someday. So have you ever wondered what happens when you click this green play button in Android Studio? So what happens is, first of all, Android Studio using Gradle and a multitude of very different plugins, it creates your APK, it compiles your code and puts in resources and creates the final APK. And then what happens is Android Debug Bridge, ADB, installs this APK on your device and then starts the specified activity, be it a default activity or a specified one using a build configuration in Android Studio. Yeah, this is basically the what you see on the screen afterwards. But then the state of this button, this little green button, changes to this one, and now it offers you not to run your application, but to apply changes to your app and restart only some part of it, only the present activity, for instance. So why does it happen, and how does Android Studio know that it's capable of doing so? It is capable of doing so because of a thing called Java Debug Wire protocol, which is used for communication between debugger and the Java virtual machine. In our case, the specific Java virtual machine is Dalvik or Android Runtime, or however you decide to call it. So what happens is there is some protocol, special protocol communication established between our development machine and our target device using either USB or IP connection if we're in the same Wi-Fi network. And so when ADB daemon on your target device starts, it creates a special server, Unix server called JDWP control. And then if the app that you're installing is debuggable, which is a special flag added to Android manifest every time you run your application from Android Studio, then a special JDWP daemon thread is started inside of your app's process. You can see it here in debugger in threads, that there is this ADB JDWP connection control thread. And then that daemon from inside of your app's process connects to this server socket that runs on your target machine. And then using port forwarding, we establish communication with our development machine, and that's how Android Studio knows that the app is running and that that special monitoring thread is running inside of that app at a given point, and it is able to attach the debugger to that process, or it's able also to run these different alternatives of just running the app, which are apply changes and restart activity. Yeah, so what Android Studio does exactly under the hood is it is using ADB. It invokes a command called track JDWP, which prints process IDs of all the debuggable processes on device. And that's how it knows that your app is running. And if it stops running because you force stop it on the device, that's how Android Studio knows that it has happened. So if you invoke that command, you see PIDs of different apps. Then if you run your app, you will see that the PID of your newly created app was added at the end of the list. And then once you close it, it disappears. Yeah, and that's how Android Studio knows that the state of the running app changes. And you may find it helpful in some special cases, like when you're working around some cybersecurity things. You can, for instance, try to debug your app using command line. I'll show you in a second how to do it. So there, at the very end of this little litany of commands that are invoked when this green button is pressed, there is also this track JDWP, which is meant for monitoring the app status, app process status. So if we create our very simple example application with a floating action button, and inside of the onClick listener, we just invoke some method that does something, we are able to debug it using a command line like this. Very simple. We just set up the forwarding from the debug wire server on our device to our hosting machine, and then we attach the debugger to a specified port on our local host, and we can type in to stop in a specified method, and once we click on that floating action button, we will see that I've clicked on the floating action button, and we can see the output from the debugger that it has hit the breakpoint on the main thread on line 33 in some method. Then we can invoke simple just everything that we normally invoke from the debugger, which is step into, step over. So in this case, I have stepped one line forward and got into the log method. Then I have typed in continue, and the app was running, not catching any breakpoint. And then if I if I've clicked on the tab again, it hit the breakpoint again. So we may find this useful in some special cases, like when you're working around cybersecurity in mobile apps, or in some very special case when you want to change some variable values using in your continuous integration pipelines, when you're, for instance, testing or checking different versions of your app and you don't want to mess with flavors or some other stuff like this. You may just use the debugger and just change your values of your variables like this using command line tools when your app is already running. There is also another interesting thing that happens when you click this button, this debug button, because there is this -d parameter appended at the end of the start command. And what it does is it forces your app to stop at this point. This is what you see if your app starts from scratch. And it's a common misconception to think that when you're waiting for too long to go past this screen, that the app is already running in the background and it's losing state. And as I said, it's a misconception. It's not true, because your app is literally stopped and suspended, because the main thread is suspended in the at line 6300 in activity thread class. You can check it if you want to. And this is way before even the constructor of the main class is called. So this is way before any activity or service or anything is started. So there's no way actually to lose any state. But it's a common misconception because we see some part of the UI already. So we may get a feeling that the app is already running, but it's not. Now, if you've ever been any close to system-level programming for instance, embedded Linux, you have probably interacted with your device using Secure Shell. And ADB on Android is way more than Secure Shell is on Linux. First of all, interestingly, Secure Shell is not part of Android. If you want to add it, if you're a system level engineer, you can do it. You can do it, of course, at the build step, but originally it's not part of Android. And it offers monitoring. ADB on top of SSH allows to monitor state of multiple connected devices, and it has lots of shortcuts for instance, pushing and pulling files, etc., etc. Regarding key-based authentication, if you ADB also has integration with other parts of Android, and this is one of the symptoms of it, because when you attach a new debugging, a new development machine, then you see this screen, and which asks you to confirm that you want to debug this device from this machine with this fingerprint, and it saves this fingerprint under this path. So it's also important to know, when we're talking about tools and tools like ADB and Shell on Android, it's also nice to know their life cycle. So let's take a look at the broader picture. So when our device boots up, first thing that starts is the CPU. And once the CPU has started, it starts the bootloader, which basically initializes RAM and loads some very basic stuff and hardware. Then it jumps to kernel, and kernel initializes hardware drivers, mounts, root file system, and then once we get out of the kernel initialization, we leave the Linux or Unix world, and we get into Android world. And this is where Android-specific things happen, like in the init process, which is the very first process that is started on the device after the kernel is started. And inside init, all of the remaining file systems are mounted, out of memory or low memory killer adjustments are set, and then various different permissions are assigned, and various different folders are created inside of init. And after the end of init, native daemons are started. And native daemons are, for instance, the boot animation, which is a very simple daemon that basically displays a set of, this is literally a set of PNG or JPEG files. What you see, the very first animation that you see on the screen is just a set of pictures displayed by the boot animation daemon. And then there are also some other native, lower level native daemons, like for Bluetooth and for media server. And the most important of these, which plays an important role in later steps of this pipeline, is the zygote. But it's important to note that ADB is started at this point. So once we leave the native daemons initialization part, we are already able to interact with ADB. And this is way before any of the Android runtime system servers or apps is started. And this is way before we are able to interact with our device using touch or visual input. And therefore we are able to interact and make changes into our system. So let me give you an example. We are messing up with some system application, for instance, launcher, or we have broken it in some way. What we can do is, for instance, once we restart our device and once we are able to interact with it using ADB, we can suspend the initialization process, or we can suspend the zygote process, which then will cause our all of the Android runtime running apps to not be started. We can try to fix them and then resume the whole process, hoping to have fixed it. So we can see that there are basically 10 steps in our boot up process, and we are able to, and that only at the step number 10 we are able to interact with the device using touch input or remote controller input, as in Android TV case, but we are able to interact with the device using shell or ADB at step number 5. So pretty early, way before any of the runtime or system services started. Now let's explore some of the less known ADB commands. And these are less known for let's say ordinary application developers, because when you just develop an app and put it into Play Store, you don't mess around with any system level programming. But if you do, and you find it interesting, you may be interested in taking a look at what you're able to do when you have root privileges. So in order to get root privileges, for instance, you can do it on an emulator. You can either invoke the ADB root command or ADB shell, and then once you're in the shell, you can switch user to root. And if you're in, you can also check if your ADB is running in secure mode. And most of the devices that are available in the retail market run their ADBs in secure mode, which prevents you from getting root privileges. But this is not the case with emulators. And this is also not the case with some specific devices from some Chinese manufacturers. They go out of the factory with having their ADB running in non-secure mode, which allows you to get root access. So if you're on a retail device like my OnePlus mobile phone, and you just invoke the process status and grab ADB, you will discover that the owner of ADB process is the user shell, and parent process ID has number 1, which is here, which means that the ADB process was started by init, which has ID 1. And then if you take a look at shell itself, you may also discover that it was that the owner of shell is the user shell, and the parent process ID is ADB. So the shell you're interacting with was started by ADB daemon on the device. And on my OnePlus, you are not able to run the switch user command, so you're not able to get root, and the same goes with ADB root command, because ADB daemon cannot run as root in production builds, which is not the case with an emulator. So with an emulator, you can see that ADB runs in non-secure mode, because secure is 0. And then if you're just normally using it, the same thing applies. So your ADB daemon is, its owner is the user shell, and the shell itself has the owner shell. But if you switch user, you'll discover that the shell that you're interacting with is now owned by root. But ADB daemon, if you do not do the same with ADB, it's still owned by shell. But if you restart your ADB as root, you will soon discover that both your ADB and shell are owned by root. And this opens very interesting possibilities. So it's a common, at least I think so, it's a common misconception to think that if you're root, it automatically allows you to mess around with all the file system, and it's not the case, because first what you have to do is remount your system partition. If you want to mess around with the system, is to remount it to read-write mode. And again, you are not always able to do it, even if you are root. But again, only then are you able to mess around with your, for instance, pre-installed apps. Now, you can reboot your device in many different modes. You can just reboot it. You can reboot to bootloader. You can reboot it to recovery if you want to, for any reason. And you can reboot your device to sideload. And this is specific to the Nexus line of devices, where you can download the system image from Google's website and just put it on your device using the sideload method. Now, once you're in Android shell and you have the command line interface, you can interact with it pretty much in the same way as with any other Linux shell. So you're capable of piping, you can do output redirection, background execution, and you can use conditional statements as well as loops. And on top of shell, there is also a multitude of different interesting binaries, or we perceive them as just commands, but they are in fact, as we perceive them as shell commands, but they are in fact libraries which belong to something called Toybox. And if you're ever been close to, again, system-level programming on Linux, you may have encountered something called BusyBox, which is, as they say, the Swiss Army knife of embedded Linux. And its equivalent on Android is Toybox. In newer Android releases, in some older ones, it was Toolbox, and these are all just some open source projects that make their way into final Android builds, just like hundreds of others, other open source projects that are part of Android. And the utilities that are part of Toybox are, for instance, process status, print working directory, remove directory. So very common commands that we use every day, but we're not even aware that they are not they're not shell commands per se, but they are just part of some other external project that in this case is Toybox. And they are binaries. In fact, every one of these commands is a separate binary, separate application. In fact, you can call it so. And as you can see, Toybox is part of Android open source project. Yeah, and it's even still contributed to. Apart from these binaries that are part of Toybox and those that are not part of Toybox as well, you can, using command line, you can also interact with various system services. In this case, for instance, Activity Manager or Logcat or Monkey. You can also directly interact with the Dalvik virtual machine, so the Android runtime. And on Android, you are basically able to run any Java application that is compiled to the Dalvik bytecode. So, for instance, it must be no higher than Java 8 and then compiled into Dalvik bytecode. And if you install such an app on Android and then you initialize it as part of your init process or somewhere, the user may never be able to even realize that there is some app running on such a device, an app like this, because it will never be listed as one of the installed apps on Android, because this would not be a technically an Android application, but yeah, this is a way to pre-install, for instance, some Java apps on Android that the user may not be even aware of. An interesting property, because Android offers offers an API to get various different get and set various different so-called system properties. And one of them is boot completed. And this is set to this is a binary property, and this is set to true only after the launcher application is started. So the first application that the user is interacting with at the end of the boot process. And this property is very important if you're ever building a continuous integration pipeline and you're dealing with emulators, and you want to run your Espresso or UI Automator or tests on your Android emulators, you have to take a look at this property and check its value in order to know when to install and start the testing process. You can also, for whatever reason, set properties, and in this case, the debug layout true shows you layout bounds. And this, again, may be important for you for some reason as part of the CI pipeline. If you encounter some bug, you can take an ordinary screenshot, and you can take a screenshot like this for maybe easier debugging afterwards. And you can also using shell, you can, for instance, interact with the package manager and ask it to, for instance, hide or unhide packages. And when you hide some package, you are not able to interact with it from the level of launcher. A hidden application will not be shown to you. From shell, you're able to interact with the file system. You can explore it. And for instance, on an emulator, if you just list all of the list the contents of the root file system, there's many pretty interesting things you can find there, and interesting file systems and folders. So, for instance, data here is a place where all the data about installed applications is stored. All of the content providers, all of the shared preferences. For instance, system is where all the pre-installed apps are, where the framework is. Vendor, for instance, is the place where implementations of hardware abstraction layers are put by vendors. And also, these are files that are, for instance, in the init.rc. If you cat this file, if you open it, you will see the whole litany of things that happen as part of the boot up process, as part of the init step. And you'll literally see a litany there that all of these catalogs, all of these folders here, all of them are created, all of the file systems are mounted, permissions are assigned to different, for different users to different places, and this is the whole initialization procedure here. Yeah, in the dev, you'll find, just like on Linux, you'll find your attached hardware devices. Yeah, and then in proc, you'll find your processes. So if you go to, for instance, the data/app, you will find the data of your installed apps. Like in my case, the example app with the floating action button is installed in such a folder. And what's there is basically the base APK that was installed, and it has also unpacked, if there are any, of course, it has also unpacked binary libraries. Also, in this specific path, you will find also shared preferences of your app, the databases, and all of the internal storage specific files, and you will also find your optimized DEX files. In a very interesting file called packages.xml, you will find installation paths of your apps. You will find permissions that every app has, and you will also find the user IDs. And if you take a look at it, you will see that system apps have a shared user ID, and therefore they are able to first of all interact with each other, and then access their memory when they are running. If you take a look at the jobs.xml file, you will find there all of the background jobs scheduled from as job services, together with their package names and together with their last successful or failed time and their constraints. And you'll, for instance, if you take a look at this file, you'll find that they're pretty. You'll find all of the listed background jobs from all of the apps that you are running and perhaps draining your memory. In the system partition, interesting paths are app and privileged app and framework. App is where all of the normal, let's say, apps are installed. In priv-app, all of the privileged apps are installed, and privileged apps, for instance, are able to interact with system level APIs, with hidden APIs that we normally cannot use as Android developers. And in framework, you can find very interesting files like framework.jar and framework.res.apk. And in the framework res APK file is where all of the resources, all of the system level or framework level resources are packed in. And in framework.jar is where all of the classes like view and context, activity, and all of the hidden APIs are contained. So if you ever encounter things like bugs, like for instance on certain Samsung or Xiaomi devices, some text view behaves a little bit differently than on every other device. This is where the difference is, somewhere in this class or somewhere in the base text view. The implementation is just a little bit different than in the stock Android open source products, and this is where these changes come from. And hopefully we will get rid of this class of problems entirely once Jetpack Compose becomes popular, because this high dependence on framework, on built-in framework, is one of the primary sins of Android. But back then, who knew back then that it will cause such problems? If you take a look at the system/bin directory and list all, you'll find all of the binaries that you're able to interact with using command line. And we can see here, like, for instance, the activity manager or some other binary that is a symbolic link to Toybox. So this is part of the whole suite of such binaries that constitute Toybox. And then if you take a look at system/xbin, you will find the switch user binary there. And of course, you can find it only on the emulator or only on the devices that you're able to get root access on. Now, getting back to system services, you can interact directly with system services from the level of command line. And an interesting fact is that on Android 10, we have 165 different system services. And let me recap a little. These are all of the services that are running on top of the Dalvik virtual machine. And you can compare it to just 65 system services that were present on Android 4.1. So we have more than double increase over, I don't know, 5 years or 6 years. And that's a lot. You can, as I said before, you can interact with your system services using command line. For instance, if you invoke the command service call statusbar1, you're able to show status bar, and if you invoke 2, you can hide it. And this 1 and 2 come from, to make the long story short, this is method number 1, and this is method number 2. And this may sound silly, but it is actually true, and it comes from the specification of the binder protocol. You're basically passing here the index of the method, and if there are any parameters, you would pass it alongside, just next to the 1 or the 2. You can also dump the state of your system services using dumpsys. In this example, you can dump the state of activity manager service, and this is a very useful command. Dumpsys activities grep run. This is a very useful command if you're getting into a new code base that you're not familiar with, and you get to some place, to some activity, and you don't know what that activity is. It gets even worse with fragments, but it's another discussion. It's a simple way to get to know in which activity you are actually. So this would be the activity index 0, the currently running one. And these are all divided here by tasks. So if you have some background activities, you can also easily debug your application this way if you ever get into some problems regarding activity grouping and tasks. This is the way to get to know exactly what is the current state of your app. So, have you ever wondered how many threads does an app like this, a very simple one, need to run? How do you think? Like 1, 2, 3, 5? Wrong. This app needs 13 threads. This is just a sample from Android Studio, very simple sample with a floating action button, nothing really interesting there. Such an app needs 13 threads to run. Why is that? First of all, you have your main thread. Just as we always know, there's one main thread. Apart from that, you have the render thread, which is a very important part of the drawing pipeline. You have your binder threads, which are responsible for communication with external system services, like, for instance, the input service, which dispatches touch input events to your app. You have your threads responsible for garbage collection, reference queue daemon, heap task daemon. You have your JDWP thread, which is responsible for monitoring the app's state. And apart from that, you have your thread responsible for saving the profile of your app, because on the newer versions of Android Runtime, your application is profiled. The bytecode is profiled and optimized so that every new start of your app is faster than the first one. And then if you create new threads inside of this app, in my case it's 5, you're able again to see them here. And this is a simple way to get to know that threads inside of Android apps and threads in Java are in fact no different than system level threads. It's not something different. They are, because the kernel of the system is aware of every thread inside every application. And it doesn't matter if it's a Java thread or if it's a native thread, it's just a thread on the system level. And the same goes with coroutines, because coroutines are not anything different on top of the already existing operating system, because what they use underneath is the thread scheduler, which uses, again, system level threads, and there's actually no magic there. And it's a misconception to say that coroutines are like lightweight threads. This is entirely not true, because they are threads in fact, but not directly, because they are dispatched on the thread scheduler. But all in all, the bottom line is that there are still threads underneath it, and the kernel doesn't really know that you are using any coroutines or RxJava. It doesn't care about that. Yeah, you can see the same picture here in your debugger window. You can see all of your threads here, and interestingly, you can pause them or suspend them, or yeah, you do many different things with these threads here. And it's also, again, interesting to know that such a simple app needs 13 threads at least. I recommend, if you're interested in the topics I've talked about today, I recommend this book. Highly recommend it. It's like 7 years old now, so pretty dated, but the basic truths still stand. I highly recommend it. The Embedded Android by Karim Yagmur. And that's it from me today. Thank you very much. I'm looking forward to your questions if you have any.
Awesome. Thank you very much.
Thank you.
That was excellent. We do have one question. So if you've got questions that you've been sitting on, start typing them in. The Slack channel is down below. The first question right now is, how is Dalvik different from ART? I thought ART was introduced around 2013-14. Do they coexist?
No, actually, well, Art is at least as far as I know, Art is an extension or a modernization of Dalvik, but some of the names that were previously just belonged to the platform, they still stand. So the Dalvik binaries that are on Android system, they are still called Dalvik, but the whole runtime is called Android Runtime now. So this is again some confusion, but this is just naming.
Gotcha. All right. Well, right now that is the only one. We'll see. One person is typing, so we'll give them a minute.
Okay.
And remember, everyone, if you don't get your question asked right now, Wojciech can pop into the Slack channel anytime today or anytime, because the Slack will stay active forever and answer any questions as well. All right. Still typing, so we will go ahead and move that over to Slack. So, Wojciech, thank you very much. Glad to have you this morning or this evening for you. Appreciate it. We will be back in about 14 minutes. So we will see everyone then. Make sure to swing by the expo, thank our sponsors, and if you're feeling brave, hop into the networking section for some random pairing with new people. Hopefully you've already met a few new folks, but if not, you still have some time. So thank you, Wojciech. Enjoy the rest of the conference.
Thank you. Thank you for inviting me.
Absolutely.